Right now, as you're listening to this, an object from outside our solar system is executing a maneuver that should be impossible. On October 29, 2025, at precisely 1400 hours, Universal Time, interstellar comet 3I, Atlas will reach perihelion, its closest approach to the Sun, at a distance of 203 million kilometers. During the 8 days surrounding this event, the object will remain completely hidden from Earth-based observation, positioned directly behind our star in what astronomers call solar conjunction. The timing is remarkable, the trajectory is remarkable, and what we're seeing in the data is forcing us to reconsider what we thought we knew about objects traveling between the stars. Here's what makes this moment extraordinary. 3I Atlas is not just passing through. It's passing through along a path that aligns within 5 degrees of the ecliptic plane, the thin disk where all the planets orbit. For an object arriving from the randomness of interstellar space, this is statistically improbable. Think of it this way. If you threw a frisbee from Alpha Centauri and it happened to skim along the surface of a pond 4 light-years away, threading perfectly through the orbits of 8 planets, you'd call that aim, or luck, or something else entirely. The discovery came from the Atlas Survey Telescope in Rio Hurtado, Chile, on July 1, 2025. Within hours, astronomers at 227 observatories worldwide turned their instruments toward this visitor. What they found was an object moving at roughly 130,000 miles per hour, nearly twice the velocity of the previous interstellar visitors, 1I Oumuamua and 2I Borisov. Pre-discovery images pushed the timeline back to May 7th when NASA's Transiting Exoplanet Survey satellite had captured it at 6.4 astronomical units from the Sun, already active, already outgassing, already defying our models. The Minor Planet Center, the global clearinghouse for small body observations, designated it 3I, the third confirmed interstellar object. The hyperbolic orbit left no doubt. Eccentricity of approximately 1.000016. That number tells you everything. Anything above 1.0 means the object is not bound by the Sun's gravity. It came from somewhere else. It's going somewhere else. We just happen to be in the way. Now here's where things get interesting. Between May 15th and September 23rd, 2025, 4,022 observations were compiled and analyzed. A team led by Richard Cloate, Peter Veress, and Avi Loeb at Harvard calculated the non-gravitational acceleration, the tiny pushes that occur when a comet sheds material and creates thrust like a natural rocket. For 3I Atlas, that acceleration measured less than 15 meters per day squared. For an object that the James Webb Space Telescope confirmed was losing 150 kilograms of material every second, primarily carbon dioxide, with an 8-to-1 ratio against water ice, that number is absurdly small. Let me translate that. Imagine a fire hose shooting water in one direction. Newton's third law says you should recoil in the opposite direction. Now imagine the hose is so massive that even with all that water spraying out, you don't budge. That's 3I Atlas. The lack of measurable recoil implies a minimum mass of 33 billion tons. At solid density, that yields a diameter exceeding 5 kilometers for the nucleus alone, not counting the coma of gas and dust surrounding it. Hubble's observations on July 21st narrowed the upper bound to 5.6 kilometers. That makes 3I Atlas at least 1,000 times more massive than 2I Borisov and potentially 1 million times heavier than Oumuamua. Here's the terrifying part. We should never have seen 3I Atlas before detecting hundreds of thousands of smaller objects. The size, distribution of interstellar debris follows predictable power laws. Small rocks vastly outnumber large ones. Given the limited reservoir of heavy elements ejected from planetary systems across the galaxy, finding an object this massive, this early in our search, is like reaching into a jar of marbles and pulling out a bowling ball on your third try. The statistical expectation was that we'd catalog something on the scale of 100,000 smaller interstellar visitors before encountering one of this scale. We've cataloged exactly 2. The Vera Rubin Observatory, which came online this summer, discovered 2,104 new asteroids in its first 10 hours of operation. Before Rubin, we were finding roughly 20,000 per year. With this detection capability, we should be swimming in interstellar objects. We're not. That's anomaly number 1. Anomaly number 2 appeared in the Hubble images. David Jewett at UCLA noticed something unusual: a forward-pointing jet, a plume of material not streaming away from the sun as comet tails do, but toward it. This anti-tail, as it's called, stretched 10 times longer than it was wide, aimed sunward with geometric precision. By late August, observations from the Nordic Optical Telescope in the Canary Islands showed the anti-tail had reversed, becoming a conventional tail. The transition occurred over weeks. Comets occasionally display anti-tails, but they're optical illusions caused by viewing geometry, seeing the dust trail edge on as Earth's position changes. 3I, Atlas's anti-tail persisted across multiple viewing angles and observation windows. It behaved, several astronomers noted, more like a directional exhaust than a dust plume sculpted by solar radiation pressure. Anomaly number 3 is compositional. Spectroscopic analysis by the James Webb Space Telescope on August 6th detected carbon dioxide, water vapor, carbon monoxide, carbonyl sulfide, and trace amounts of nickel. The nickel to iron ratio was inverted compared to solar system comets. Nickel exceeded iron content by measurable margins. This signature resembles industrial nickel alloys more than primordial ice. The carbon dioxide dominated the outgassing, which explains the early activity at 6.4 astronomical units, well beyond where water ice sublimates. Dry ice vaporizes easily, but the sheer volume of CO2 relative to water, that 8-to-1 ratio, suggests formation conditions radically different from our solar system's comet reservoirs. It's a glimpse into how another star's planetary system assembled billions of years ago, or it's something else. Anomaly number 4 involves timing and trajectory. 3I. Atlas will pass within 29 million kilometers of Mars on October 3rd, within 97 million kilometers of Venus on November 3rd, and roughly 54 million kilometers of Jupiter on March 16, 2026. The minimum orbit intersection distance with Mars, the closest 3I, Atlas's entire orbital path approaches Mars's entire orbital path, is just 2.7 million kilometers. That's fine-tuning. Meanwhile, Earth remains safely distant, with the closest approach occurring December 19th at 269 million kilometers. The object threads planetary orbits with precision, coming close to worlds with orbiters and landers while avoiding direct Earth interaction. And then there's the conjunction. October 21st through late October, 3I. Atlas sits directly behind the Sun from Earth's perspective, unobservable. This is when perihelion occurs. This is when solar irradiance peaks, delivering approximately 33 gigawatts of power to the object's surface, equivalent to 1/3 of the United States' total nuclear power generation. In orbital mechanics, there's a concept called the Oberth effect. If you want to change your spacecraft's velocity efficiently, you burn fuel at the moment of highest speed, at closest approach to a massive body. Perihelion during solar conjunction is textbook Oberth timing. It's also textbook for a natural comet heating up and potentially fragmenting. Let that sink in. I want to be clear about what we're dealing with. The baseline hypothesis is that 3I, Atlas, is a natural comet, an ancient relic ejected from another planetary system during its formation, wandering the galaxy for hundreds of millions of years before intersecting our solar system by pure chance. The evidence supports this. It has a coma, it has a tail, it outgasses. Webb confirmed cometary volatiles. NASA's Tom Statler, program scientist for the Solar System Exploration Division, stated unequivocally that it looks like a comet, behaves like a comet, and is almost certainly a comet, just one with properties reflecting its extrasolar origin. Jacqueline McCleary at Northeastern University emphasized that these interstellar comets are the only physical samples we've ever obtained from beyond our solar system, invaluable for understanding planetary formation diversity across the galaxy. The data supports the natural explanation. The data also refuses to make it easy. Consider 3 scenarios, 3 frameworks for interpreting what we're observing. Scenario 1. 3I, Atlas is exactly what it appears to be, a carbonaceous comet rich in CO. 2. Formed in a planetary system where carbon dioxide ice was abundant and water ice was scarce, perhaps a system with a cooler stellar host or a different volatile distribution during protoplanetary disk evolution. The size is unusual but not impossible. Comet Bernardinelli-Bernstein, discovered in our own Oort cloud, has a nucleus 128 kilometers across, dwarfing 3I, Atlas. Large comets exist. The trajectory's ecliptic alignment is rare, but explainable through gravitational perturbations and selection bias. We're more likely to detect objects moving through the plane, where most of our observatories concentrate. The anti-tail reversed as expected once viewing geometry and outgassing dynamics equilibrated. The high nickel could reflect primordial abundances in the parent molecular cloud. Everything fits, given sufficient parameter space. Scenario 2. 3. Atlas is a warning or a probe, not in the sense of directed intelligence but as an unintentional herald. Its mass, trajectory, and composition tell us that planet formation in other systems produces outcomes wildly different from ours. The statistical improbability of detecting such a massive object so early implies our models are wrong. Perhaps interstellar space is filled with debris larger and more numerous than we calculated. Perhaps ejection mechanisms are more efficient than accretion theory predicts. The object itself is natural, but its existence forces us to revise fundamental assumptions about galactic material budgets. It's a data point that doesn't fit the curve, which means the curve is incorrect. We're being told by the universe that we don't understand the architecture of planetary systems as well as we thought. That should concern us more than any alien hypothesis. Scenario 3. 3I, Atlas is under some form of non-natural influence. Not a spacecraft in the Star Trek sense, but an object that has been modified or is being guided, perhaps a billion-year-old relic from a long-dead civilization, dormant for eons, responding to solar proximity with pre-programmed behavior. Perhaps a Bracewell probe, a self-replicating explorer designed to visit stellar systems and lie dormant until triggered by specific conditions. The anti-tail could be active deceleration. The perihelion timing during conjunction could be deliberate, using the sun as a gravity assist or energy source while remaining unobserved during critical maneuvers. The lack of non-gravitational acceleration, despite massive outgassing, could indicate internal compensation, a core dense enough or a structure hollow enough to resist the rocket effect. The trajectory's alignment and planetary close approaches could be intentional. This third scenario ranks a 4 on the Loeb scale, a metric proposed by Avi Loeb for quantifying the likelihood of technological signatures. Rank 4 means unusual but not conclusive, warranting systematic follow-up. It does not mean aliens. It means we don't dismiss the possibility prematurely while maintaining the natural baseline. Science is not about believing, it's about testing. And we're about to run the most important test in this object's brief observation window. Here's what's called the improbability stack. Individually, each anomaly has a natural explanation. The size? Rare but possible. The mass to outgassing ratio? Depends on density and porosity, which we haven't measured directly. The trajectory? Selection bias? The anti-tail? Viewing geometry plus asymmetric outgassing? The nickel? Primordial chemistry? The conjunction timing? Coincidence? Stack them together, though, and you're compounding low probability events. 5% chance times 10% chance times 20% chance times 15% chance equals a very small number. This is Bayesian reasoning. Each additional improbable feature updates our confidence in the baseline hypothesis downward. Not enough to abandon it, but enough to pay attention. And we are paying attention. On October 3rd, the HiRISE camera aboard NASA's Mars Reconnaissance Orbiter attempted imaging at a resolution of 30 kilometers per pixel. That's enough to distinguish the nucleus from the surrounding dust cloud, to measure the true size, and potentially detect secondary objects, precursor probes, if such things exist. ESA's Mars Express and ExoMars Trace Gas Orbiter joined the effort, deploying the high-resolution stereo camera, Omega spectrometer, SpyCam spectrometer, and Nomad spectrometer. The goal was spectral characterization and volatile composition mapping during close approach. Mars is our forward observation post. November 4th, ESA's Jupiter. Icy Moons Explorer, JUICE, will pass within 64 million kilometers of 3I Atlas. JUICE launched in 2023, currently en route to the Jovian system, but perfectly positioned for this encounter. It carries cameras, spectrometers, and particle sensors. Coordination with NASA's Europa Clipper is being considered, particularly for twin ultraviolet spectrograph observations. JUICE's data won't reach Earth until February 2026 due to communication bandwidth and solar geometry, but when it does, we'll have multi-wavelength coverage of 3I Atlas in a highly active state, post-perihelion, potentially fragmenting or deploying material if it's going to do so. December 19th, the object's closest approach to Earth at 269 million kilometers. By then, it should have re-emerged from behind the Sun, visible again to ground-based telescopes and Hubble. The question is whether it re-emerges intact or fragmented, whether its outgassing continues or ceases, whether its trajectory shows any deviation from the gravity-only prediction. If 3I Atlas performs an Oberth maneuver during perihelion, even a small velocity change, 10 to 15 kilometers per second, would be detectable in post-perihelion tracking. That's the smoking gun. A trajectory correction that can't be explained by outgassing would force Scenario 3 into serious consideration. March 16, 2026, the Jupiter flyby. Juno spacecraft, in orbit around Jupiter since 2016, has ultraviolet, infrared, and radio instruments ideal for comet observation. This will be our last detailed look before 3I Atlas leaves the inner solar system forever, accelerating back into the interstellar medium at hyperbolic velocity, never to return. What should we watch for? Pattern changes. If 3I Atlas resumes the sunward jet after perihelion, if the anti-tail reappears, that's notable. If the outgassing stops abruptly despite continued solar heating, that contradicts cometary models. If Hubble or Webb detect structural changes, breakup, or deployment of subcomponents, that's critical data. If ground-based observations in November and December reveal secondary objects trailing the nucleus, mini-probes on diverging trajectories, that moves us into uncharted territory. If trajectory analysis post-perihelion shows anomalous acceleration unaccounted for by mass loss, we have a problem that demands explanation. Fragmentation is expected for comets under thermal stress. Comet Shoemaker-Levy 9 broke into 21 fragments before colliding with Jupiter in 1994. Thermal fracturing, structural weaknesses, tidal forces all contribute. If 3I Atlas fragments, that supports the natural hypothesis. If it doesn't, if it emerges intact after 33 gigawatts of solar irradiance and 2 million tons of mass loss, that's structurally remarkable, but still explainable by internal cohesion. What we're looking for is behavior that doesn't fit, directed motion, energy release inconsistent with sublimation, radio emissions, geometric structures in reflected light, changes in albedo or polarization that suggest surface alteration rather than dust coverage. The extreme negative polarization already detected is unusual, rank 4 unusual, but not definitive. More data clarifies or deepens the mystery. I've spent my career studying the universe's most extreme phenomena: black holes, neutron stars, quantum entanglement, parallel universes as solutions to Schrödinger's equation. I approach extraordinary claims with proportional skepticism, not because I lack imagination, but because the universe is strange enough without embellishment. 3I Atlas is strange, demonstrably, measurably strange. Whether that strangeness is natural or something else depends entirely on data we haven't collected yet. The Vera Rubin Observatory will revolutionize this field. 1 to 2 interstellar objects per year, potentially dozens as sensitivity, improves. If they're all like 3I Atlas, massive and aligned, we have a galactic architecture problem. If most are small and randomly oriented, 3I Atlas becomes a true outlier, statistically significant in its weirdness. Sample size matters. There's a philosophical dimension here that transcends the immediate question. Whether 3I Atlas is a comet or something more, its existence confirms that we live in a galaxy filled with travelers. Objects ejected from billions of planetary systems over billions of years, wandering the void, occasionally intersecting other stars, sometimes ours. We're part of a cosmic exchange program we didn't know we were enrolled in. Every interstellar visitor carries information, a message in its composition and structure about conditions elsewhere, about the diversity of outcomes when gravity collapses gas clouds into stars and planets. If we find evidence, definitive evidence, that 3I Atlas is technological in origin, the implications cascade. We're not alone. We've never been alone. Intelligence is out there, or was out there, building things that last longer than civilizations. The Fermi paradox collapses. The question shifts from where are they to when were they and what happened to them. A billion-year-old probe suggests a species that achieved interstellar reach and then went silent. Why? Extinction, transcendence, loss of interest, and if they sent probes to every promising star system, how many others are out there, dormant, waiting? On the other hand, if 3I Atlas is entirely natural, if every anomaly resolves into known physics given sufficient data, that teaches us something equally profound. The universe is weirder than our models predict. Chemistry is more diverse, planet formation more chaotic. Our sample size of 1, this solar system, led us astray. We need more data. We need more visitors. We need to build better detectors, faster response protocols, and maybe eventually interception missions. Imagine launching a probe to rendezvous with an interstellar object, to land on it, to analyze it in situ before it leaves. The technology exists. The political will does not yet. In 2017, Oumuamua surprised us. In 2019, Borisov confirmed that interstellar comets exist. In 2025, 3I Atlas is forcing us to confront the limits of our models and our assumptions. Each visitor teaches us something. Each visitor asks questions. Right now, as 3I Atlas approaches perihelion, hidden behind the sun, we're in a data blackout. Instruments are ready. Spacecraft are positioned. Astronomers are waiting. The object will emerge, or it won't. It will behave as predicted, or it won't. In science, the best moments are when we genuinely don't know the answer, when the experiment could go either way, when the universe gets to vote. November through December, we get the results. If you want to stay informed as this unfolds, as observations resume, and data gets analyzed, following developments is crucial because the timeline matters. This isn't a story that will wait. By February 2026, when JUICE's data arrives, we'll know significantly more. By March, after the Juno flyby, we'll have the full picture. This is a once-in-a-lifetime observation campaign, the third interstellar object ever detected, the largest by far, moving through our solar system right now, executing a trajectory that threads planetary orbits with precision during an 8-day window of invisibility. Whether you interpret that as cosmic coincidence or something more, the data will speak. Here's the question I want you to consider. Are we witnessing the natural behavior of an ancient comet, a relic from a planetary system billions of years old, carrying information about stellar chemistry and planet formation in its composition? Or are we watching something that was launched, deliberately, with intent, to do exactly what it's doing, to visit stars, to observe, to report back to builders who may no longer exist? The answer matters, not just academically, existentially, contact or pattern seeking, signal or noise. The data is ambiguous enough to support both interpretations and definitive enough to rule out neither. That's the worst and best position for a scientist. Worst because ambiguity is uncomfortable. Best because it means we're learning, adapting, updating priors based on evidence. The history of astronomy is filled with misidentified phenomena. Pulsars were briefly called LGMs, little green men, before we understood them as rotating neutron stars. Fast radio bursts seemed artificial until we mapped their distribution and recognized natural magnetar physics. Every anomaly that felt technological eventually resolved into novel but natural astrophysics. But every novel astrophysics started as an anomaly. Exoplanets were considered unlikely until we found thousands. Interstellar objects were theoretical until we detected them. The James Webb Space Telescope is finding galaxies that shouldn't exist according to our timeline of cosmic structure formation. The universe keeps surprising us. The Nova 10.1 3i Atlas is a surprise. The magnitude of the surprise depends on what we observe next. I'll be watching the November data releases closely. Hubble spectroscopy results on gas composition, ground-based photometry tracking brightness and coma evolution, trajectory refinements from the Minor Planet Center, ESA's Mars orbiter spectra. Every data point updates the probability distribution. Natural comet remains the overwhelmingly favored hypothesis, 99% confidence or higher among the professional astronomy community. But that 1%, that sliver of parameter space where something unusual is happening, is large enough to justify investigation. That's not speculation, that's protocol. The scientific method doesn't care about preferences, it cares about reproducibility, falsifiability, and evidence. Right now, the evidence shows an interstellar comet with properties that are outliers across multiple metrics. The burden of proof for an extraordinary claim, a technological origin, is rightly enormous. We need extraordinary evidence, but we also need to collect that evidence before dismissing the hypothesis. Dismissing without data is dogma. Accepting without evidence is fantasy. Science is the narrow path between. We're walking that path right now. October 29th, perihelion. November emergence. December close approach. March flyby. The timeline is set. The instruments are ready. The only variable is what 3i Atlas does next. If it fragments, if it outgasses conventionally, if its trajectory remains gravity-dominated, we'll have confirmed a natural origin and learned volumes about interstellar comet formation in carbon-rich environments. If it does anything else, anything anomalous, we're in new territory. Either way, we win. We learn. That's the essence of science. Curiosity bounded by rigor, imagination tempered by evidence. 3i. Atlas is giving us the opportunity to test both. An object from another star system, carrying material billions of years old, executing a path through our planetary neighborhood, observed by humanity's most sophisticated instruments, at our moment of technological capability to actually analyze it. 50 years ago, we'd have missed it. 50 years from now, we'll have routine interstellar object detection and perhaps interception capability. We're right at the threshold. The question remains, are we alone? 3i Atlas won't answer that definitively. No single object can, but it's a data point. A massive, fast-moving, strangely behaving data point that's forcing us to ask better questions and build better tools to answer them. Whether it's natural or not, it's a messenger from elsewhere, telling us that the galaxy is more connected, more dynamic, more filled with travelers than we realized. The universe is speaking, we're learning to listen. So as 3i Atlas rounds the sun, hidden from view, undergoing thermal stress and gravitational acceleration at its moment of closest approach, we wait. We wait with telescopes aimed and data pipelines ready. We wait with models that predict one outcome and imaginations that consider others. We wait because the universe is full of phenomena we don't understand yet, and the only way to understand them is to watch, to measure, to think, and to test. November will bring answers or more questions. Probably both. Stay skeptical, stay curious. And stay tuned, because whatever 3i Atlas is, wherever it came from, whatever it's doing out there beyond the sun's glare right now, it's real, it's measurable, and it's challenging us to think harder about what's possible in a galaxy with 400 billion stars and untold trillions of worlds, where matter moves between systems, where timescales dwarf human comprehension, and where the next interstellar visitor might teach us something we never imagined we needed to know. The countdown is running. The object is in position. The observation window opens in weeks. This is happening now, in real time, in our solar system, during our lifetimes. Whether it's the third natural interstellar comet we've detected or something more, it's extraordinary. And the only way we'll know for certain is to collect the data and follow where it leads. That's science, that's discovery, and that's why even after decades of studying the cosmos, I still get excited when something this strange crosses our path. Because every anomaly is an opportunity, every mystery is an invitation, and every interstellar visitor, whether rock or ice or something we haven't categorized yet, is a reminder that we're part of something immeasurably larger than ourselves, something ancient and ongoing, where the rules are written by physics and the outcomes are determined by observation. 3I Atlas. Third interstellar. 33 billion tons, 5 kilometers diameter, 8 anomalies. Rank 4 on the Loeb scale. Perihelion, October 29th. Re-emergence November. Closest Earth approach December 19th. Jupiter flyby March 2026. Natural baseline hypothesis. Technological possibility remote but non-zero. Evidence pending. Questions multiplying. Are we watching a comet or are we watching something watch us? The data will tell us soon.